Here's a fun demonstration on the resonance or standing waves within an air column. Here's the website up here. You can go play with it if you would like. That would be fine. It's also available on Falcon Online. You could either deal with a tube that's closed at one end or open at both ends. We're going to start off by saying it's open at both ends. Okay, so let me just show you what's going on at first. Let's go ahead and push run. Let this thing go. We're going to show a wave. So I'm sending a wave down this tube. Well, because of resonance, there's going to be a little bit of reflection, so waves come back. And sometimes they interfere with each other constructively like you do here, and sometimes destructively like you do here. So if we show their sum, you can see that they're constantly going between constructive interference and destructive interference. Constructive, destructive, constructive, back and forth, back and forth. Now, down here in this figure, you can see the total wave of just the wave and the first 5 reflections. And you can see not much is happening. Now we have a tube that's open on both ends, so remember that the fundamental frequency is at 2 times the length of the tube. So let's set this at, say, 2. Let's go with, let's see, can I go up to 6 here? Yes, I can. So let's set the length of the tube at 3, which means that the wavelength is then going to be, I guess I can do this, set the wavelength there. Now watch what happens here. Remember that the blue line is your original wave, and the red line is your reflected wave, and the green would be the sum of the two. This causes a resonance pattern within the tube, which then causes it to vibrate, and you can actually hear that sound. You can see here in the second figure, yes, you get the most amount of vibration here. Now that's the fundamental frequency. The second harmonic would be 2L over 2. In other words, just L, so the wavelength is going to be the length of the tube itself. So here you can see the motion of the waves themselves a little bit better, blue moving to the right, and red would be the reflected wave moving to the left. And their sums would just create a full wavelength, a resonance pattern. That's your second harmonic. The third harmonic would be 2L over 3, so 2L would be 6, divided by 3 would be 2. So let's drop this down to 2. I guess I can type that in and run that, and you get yourself a third harmonic where you have 1, 2, 3 nodes. You have 3 nodes. All right, and then the fourth harmonic would be 2L over 4. 2L would be 6 divided by 4 would be 1.5. And here you have fourth harmonic with 1, 2, 3, 4 4 nodes. Now if we change that to being closed on both ends, you can see that right away, just capping it on the end, you get a little bit of resonance, but not much. Definitely the amplitude's not as high. The fundamental frequency would be 4 times the length of the tube. So let me drop this down to 2 so that we have enough room to get our fundamental. Okay. So our fundamental frequency would happen at 8. So there's your fundamental frequency in a closed tube. The first overtone would be the third harmonic, 4L divided by 3. So 4L is 8 divided by 3, 8/3. That'd be 2 2/3. So 2.67. There's the third harmonic, or the first overtone. And the second overtone would be the fifth harmonic. 4L divided by 5. 4L would be 8 divided by 5. 8/5 would be 1.6. And there you are. And we can see the seventh harmonic would be 4L over 7. So 8 divided by 7. 8 divided by 7 would be just over 1. It's somewhere around here. I don't have the exact number with me. See, I didn't quite get it. Maybe to the left a little bit more. That's pretty close right there. But if I'm off at all, my wave inside the tube gets to be a lot smaller, and so the sound does not actually go through. So I will not actually hear any sound frequencies at this particular sound waves at this frequency because they're not resonating in the tube. Anyway, that's just a fun little demonstration on the sound waves in a tube.